Hey, Cheryl. So, quantum computing, right? Like, it's everywhere. Feels like, is it actually going to, replace every computer we have?
Oh, Heidi, that's such a common question. And honestly, the answer is a big no, not really. It's actually kind of interesting, the whole narrative. It's really shifting. For a while, there was this massive hype. You'd hear people like almost prematurely promoting it. And that got some folks worried about a quantum winter, kind of like what happened with AI, right? A quantum winter. Wow, that sounds chilly. So it's not going to just poof, replace everything? Exactly. The consensus now is it's not a replacement, it's a complement. We're actually seeing it in what Gartner calls the innovation trigger stage, which means it's showing huge promise, attracting tons of investment, but it's still maturing. The hype, though, it's giving way to the really hard work now, laying a solid foundation for actual utility. Some people even think it'll be the next big hype wave around 2026, especially with post-quantum readiness becoming so urgent because of Harvest Now, Decrypt Later attacks.
Okay, so it's a complement. That makes a lot more sense. But then, what is it actually good at? Like, where does it really shine, if it's not just a super fast version of my laptop?
Oh, that's the cool part. Quantum computers are like precision tools. They're amazing at problems with massive state spaces, super complex optimization, or probabilistic systems that just grow exponentially. Think about it. They can actually pull more information from smaller data sets, which is huge for things like optimization, where data can be really scarce or just plain expensive to get.
Fascinating. So it's about like quality of information over quantity of raw processing power in some ways? Give me some examples, Cheryl, like what kind of problems?
Absolutely. In finance, we're talking portfolio optimization, spotting fraud, risk analysis, and material science, like analyzing molecular stuff, lithium battery degradation, drug discovery, screening bigger molecules, even smart cities like traffic flow optimization or supply chains, and climate change analysis and accelerating single cell biology. It's all about hitting those bottlenecks where classical systems just kinda, well, stumble.
Wow, those are some seriously impactful areas. So, if it's a complement and a specialized tool, how does it actually work with classical computers? Is it a whole new system or do they, chat back and forth?
That's exactly it, Heidi. The future, it's totally hybrid. We're talking deliberate, problem-specific integration into existing classical ecosystems. Think about it. Classical processors will frame the problem, right? Then, the quantum processors come in to solve the absolute trickiest, most complex bits. And then, classical systems take those results, interpret them, and act on them. It's like a super smart tag team.
So, like a brain and a specialized muscle working together? Precisely. We're seeing layered architectures emerge. Quantum system controllers turn qubits into functional QPUs, and then bounded latency CPU-GPU servers handle things like online calibrations. It's all about real-time orchestration, mid-circuit measurement, and quantum feedback. Take VQE algorithms in quantum chemistry, for example. They just ping-pong between quantum machines and classical supercomputers to find the lowest energy states. It's really quantum augmenting classical, where quantum handles the dense data and classical systems manage the sparse data for faster, more accurate results.